Hi everyone, my topic is cellular automata and its applications. So what's cellular automata? It's a discrete model studied in computability theory of cell objects. Each cell, like this one, lives in the grid and has a particular state. In this case, this is the grid and this state is off. It's surrounded by a bunch of other cells who are referred to as the neighborhood. Each time step taken, all cells change state according to some rules, which we'll see later, that are based on the states of the neighboring cells. So if we take a look at this animation, this is a bunch of cells turning on and off according to the cells that are surrounding a particular cell. This is a more clear example of just that. So let's get into its applications. The first one is cryptography. One of the main problems in cryptography is generating a true random number, which is not very random as it is because it's based on mathematical models. With enough time, we can derive mathematically or logically what the key could be for a certain security. Just like this function, get random number, right? We can right away tell this is not very random. So a proposed solution using cellular automata is best exemplified through Conway's game of life. It's made up of simple rules that can generate very complex behavior. And although it's deterministic, it's not reversible the way mathematical equations are. The only way to get the key for the encryption is if we somehow figure out what the initial configuration is of a cellular automata. We take a look at this picture. Right now it's getting almost done. Starts out somewhere here, right? And then according to the position of each cell and whether the state is on or off, it generates a complex behavior in this direction and another complex behavior in this direction, which is what cryptography wants. These are some of the rules that I mentioned earlier. As you can tell, these are very simple rules. This is written in pseudocode. Depending on whether or not certain cells are alive or dead, results in a single cell either dying or coming to life or staying as it is. This, of course, generates a pattern very closely resembled to this. Now, I wrote a simple Java application that can also better exemplify this example. Let's run it. And what we're going to have here is a grid that's generating with a very similar set of rules as what I just showed you, so that these can move. This is the only one that's sort of moving all the way to the corner until we can no longer see it. And this just sort of keeps going. So what we'll see next is another application of cellular automata, which is modeling and simulation. Currently, a lot of modeling and simulation is done using heavy math, equations, computations, but given the simplicity of cellular automata and its complexity that it ends up producing, it seems very fitting to do a lot of the modeling and simulation using Cellular Automata. Here we have an urban development of Ontario from 1985 to 2010. And then here we have a forest fire that starts out somewhere around here and that keeps spreading and spreading and spreading. And of course, a bunch of other applications like gas behavior. Each molecule depends on the status of the molecule right next to it. Turbulence in fluids, crystallization, flow of electricity, and of course, life itself. The reason why this works so well with modeling and simulation, it's because it starts with very simple rules, and it starts with very simple pieces to end up creating a very complex or global picture. For example, the forest fire starts with one burning tree, and then the surrounding trees, and the surrounding trees of those surrounding trees, and so forth. Wolfram points out a very similar concept. Cellular automata are inherently more efficient at analyzing many natural systems than traditional computational methods, because these mechanisms found in most natural systems are close to those of cellular automata than conventional computation. And then of course there's artificial life. This is probably the #1 application of cellular automata. Cellular automata can help explain how complex systems, like life, emerge in a universe of entropy. So here we can compare just a couple points between cellular automata and life. The first one is, given an appropriate lambda expression or condition, it can result in self-reproduction, kind of like how we saw earlier in the Java program and the little animations I showed you guys. This is equivalent, of course, to given some right conditions in life, reproduction is possible, right? And then the second similarity here is, based on simple rules, we can drive complex generations from what initially was a few cells. The equivalent similarity for life is emerging from simple molecules that can push evolution to enable some sort of complexity. One of the final aspects of this, of course, is art. People have fun with it. Because of the iterative and hierarchical nature of cellular automata, art can be created. We have things like this, a bunch of cubes replicating themselves. We have stuff like this, a bunch of triangles forming to make bigger triangles. And then we have cool patterns like this. Now, there's a site that allows you to further play with this. Conway's Game of Life, right? We can run it, and we can see all these cells turning on and off, on and off, on and off, until they somehow reach a dead end. You can change what kind of simulation it runs. And people get very creative with this. Let's go back. And of course we have many more different types of arts that people make to either just express themselves or try to express an idea just like life. Probably used in biology a lot. Thanks for watching.